Hello, my name is Jason Morales, and I'll be explaining my design process for the final. So first, we're given this open loop transfer function. It has to meet the requirements that I'm showing on the left. The percent overshoot has to be less than 30%, a rise time of less than 0.15 seconds, a steady state error of less than 0.1, and a phase margin of greater than 60 degrees. So the first step I did was to plot the Bodhi diagrams and the root locus. And on the root locus, the branches only stay on the right-hand side of the plane, so the system is always going to be unstable. There's no value of k of a gain that will make it stable. And then on the Bodhi diagrams, the magnitude is always below 0 decibels, so it will never have a crossover frequency. So to stabilize this, I decided to make a lead compensator. And this lead compensator is focused on increasing the phase margin and not trying to intersect a specific dominant pole, because if the first phase lead compensator isn't enough to achieve the proper phase margin, then we would need another lead compensator and it would change the dominant poles. So focusing on the phase margin, we would need a crossover frequency first to make one. And we can find a crossover frequency if we can find a gain for the original transfer function. So I found this gain using the steady state error of less than 0.1. So I have here the equation for steady state error with a step input. And solving for the gain, it would give us, the gain would need to be greater than 83.25. But I set it to 84, so the gain is, or the steady state error is very slightly less than 0.1. So next, we have a crossover frequency. So after we plotted the given open loop transfer function with the gain, now we have a crossover frequency at 9.6 radians per second, but our phase margin is negative 6.5 degrees, which is much less than the 60 degrees. So since we are in a deficit of about 66.6 degrees on phase, and the maximum that we can increase phase is about 55 degrees, I set the phase gain from the phase lead compensator to 55 degrees and solve for alpha. And solving for alpha gives me a value of 10.059. And since it's greater than 1, that means it's applicable to a lead compensator. And then I solve for the other variable tau using my alpha and the current crossover frequency, and tau gives me a value of 0.0327. And into the general equation for a compensator, I get this transfer function for my first compensator. So I have basically our current loop transfer function of GC1G is shown here, and I plotted the root locus and the Bodhi diagrams are both below. So on the root locus, the branches now cross into the left-hand side, so the system is now stable. And the Bodhi diagrams, I have some here. The phase margin is now about 43 degrees, but it is still less than 60 degrees. So we would need to have either a lead compensator or a lag compensator to achieve this the proper phase margin. And I don't know if you can see it, but on the phase Bodhi diagram, the maximum phase possible is about 50 degrees at this point, meaning that if we were to use a lag compensator, it would still not achieve the required phase margin that we would need, so we would need to use another phase lead compensator. So I'd use the same steps to design it, except now the crossover frequency is at 22.7 radians per second, and with the same process I get an alpha 3.69, which is also greater than 1, so it satisfies the lead compensator requirements, and then a tau of 0.0229. And then so this is our second lead compensator and our new loop transfer function, which I plotted here. The system is still stable, but now on the phase Bodhi diagram, our phase margin is now 59.87 degrees, which is barely below the required phase margin. So I decided to use a phase lag by shifting the crossover frequency to the left, I'll have a sufficient enough phase margin without changing the steady state error. So yeah, that's what I did next. At around, where is it? Yeah, at around this point here, the phase margin would be about 71 degrees at and this is about a frequency of 31 radians per second, which is more than the required 60 degrees. And the corresponding magnitude is about 3 decibels. So at 3 decibels, if I want to shift the magnitude down 3 decibels, I solved for that alpha again, which turned out to be 0.7079, which is less than 1, so it satisfies the phase lag compensator requirements. And then for the next step in the design process, I chose 30, which is slightly less than the 31 radians per second at that desired crossover frequency, and divided by 50, so it's significantly to the left, so the phase drop does not impact the location of where I wanted the phase margin to be at. So I solve for the variables. That gives us a value of tau of 2.3542, and our new, plugging into in our equation, our new lag compensator is shown here, and our total and our entire loop transfer function is shown here. So now, yeah, here's the plots. So now the phase margin is 69.75 degrees, and it also satisfies the steady state error because we didn't change the gain, because a phase compensator in this format does not change the steady state error. Yeah, so it satisfies the steady state error and the phase margin requirements. So now we can check to see if it satisfies the other two requirements. And we should do this before having to add another compensator. So looking onto the root locus of our final loop system, loop transfer function, I solved for the minimum zeta, or the minimum damping function that we would need. I'm using this equation, which needs to be less than 30%, and that gives me a value that the damping has to be greater than 0.357. And then looking at the root locus, at this point where the gain is 1, because we didn't solve for another gain throughout for the closed loop system, gain is essentially 1, and our damping is at 0.592 at this point. So currently it's without solving for another gain, the damping ratio is satisfactory, so the percent overshoot is okay. And then if we check to see the rise time is satisfactory, I solved for the minimum value of the natural frequency required, and I got 18.25, which is less than the 52.5 of the natural frequency that's shown at this point. So the system satisfies all requirements. And then lastly, I have here the Nyquist diagrams. On the left is the full one, and on the right zoomed in onto point -1. And then so this distance is still rather short, so the system is pretty sensitive to changes in LS in the loop system. And on the Bode diagram, the phase margin is 0.0474 decibels, which is really small compared to the phase margin of about 69 degrees that we have. So it's sensitive.